Anybody have? Okay, let's go through it. So a 10 kilogram mass undergoes a collision with the floor that lasts 0.03 seconds. Before the collision, it has, okay, so here's what's happening. There's the floor. Before the collision, if that's the vertical line, it's coming in at an angle of 10 degrees from vertical. So if that's another vertical line, then this is 10 degrees. And then it makes contact with the ground. And then after the collision, it's 20 degrees from vertical. By the way, here's the detail thing. Anything in free fall is moving in a parabolic path. So there's no way that this ball is moving along those two straight lines. So what do those two straight lines represent? Yeah, instantaneous velocity, the instant before the collision and the instant after the collision. That's what it says, right? After. Oh. I looked at a different problem there. 12, yes. Okay, 12 degrees. And coming in, it has a speed of 10 meters per second. And leaving, it has a speed of 8 meters per second. And we want the average net force and then the contact force. This mass is 10 kilograms. And the length of time, the duration of this impact is 0.03 seconds. Okay, we know that the impulse momentum equation says that if you integrate the force with respect to time from T1 to T2, that's equal to the change in the momentum, not the position vector, and so if we assume that F is constant, that says that the net force vector excuse me, times the change in time is equal to the change in momentum. And you can write that as the average net force is equal to the change in momentum divided by the change in time. So we need to calculate the change in momentum. We know that the change in time is 0.03 seconds. The momentum after the collision, because the change in momentum is going to be the momentum after the collision minus before the collision, right? So after the collision, we have to figure out that velocity vector and multiply it by the mass. So that's going to be the mass of 10 times the velocity of 8 times cosine and sine of what angle? Does everyone agree with that? If Jill says something, then you should, if you didn't listen, then you should say you agree, but it would be better if you listened and answered based on what you were thinking. Don't you agree, Meredith? Yeah. Okay. So, okay, 78 degrees. And then the momentum before the collision is the mass of 10 times speed of 10 times cosine and sine of what angle for before the collision? Yeah, perfect. Okay, so can someone calculate that? 224 for, this needs to be a vector. Oh, that's the first component? 24.296? Okay, 40, yep. Hope that should come out positive.
Yeah, that's what you had on your solution, but
Oh.
I think that's because you switched, you did P1 minus P2.
Oh, you don't do what I did.
I got negative 26.67 and 5,893.3.
5893.3.
Yes.
Yeah, so a change is always the later thing minus the earlier thing. So it should be negative for X and positive for Y. And if, I mean, think about the direction of the force. If that thing's flying down towards the ground and you don't apply any force to it, it keeps moving down. So the ground has to apply an upward force to make it change directions. So that's part A. And then part B, now we want to separate, this is the net force on average. Now we want to separate out the contact force from the weight force. So a free body diagram of ball while it's in contact. That flat part is the contact with the ground, you know. So there's a downward force of 10 times 9.81. And then there's a contact force that we can split up into a vertical and a horizontal part. I'll call it Rx and Ry. We're trying to calculate that reaction force, that contact force R. So we know that this vector, Rx, Ry, the contact force, plus 0, negative 98.1, is equal to the net force we just calculated. So that's negative 24.4, 5893.3. And so the contact force for X?
Yeah.
Okay, so the contact force is equal to negative 26.60, and then this 5893 plus 98.1 is 5991.4 newtons. So the contact force is bigger than the net force in the y direction because it has to make up for the fact that gravity is going the other direction. And it's often the case that the the shorter the amount of time the impact takes, the more negligible the weight is, and the more better an approximation the net force is of the contact force. So, like for example, if a bat's hitting a baseball and hitting it hard, or a golfer's hitting a golf ball or whatever, the weight is a negligible part of that net force because the net force is just so big compared to that. So you can a lot of times just approximate the contact force by the net force and not take this step. Any other questions about this one? Any other homework questions? Okay, so yeah, turn in your homework if you have it. Up to this very point, right now, we have treated every object as a particle. That's what we're going into now, yep. Yes. Up to this very point. So this is a historic moment right now. No, that's not a pun. Oh, okay. Well, it's not intended. We've treated every object as a particle. So what is a particle? Yes. Yep. It does have direction. That means we've treated it as having no length dimensions. And no orientation. And for some applications, that's a useful approach. Like a lot of times, if you're trying to calculate the motion of planets or something, you don't care what part of the planet is facing what direction at what time, But at other times, the same objects, you do care about the orientation. Like if you're trying to figure out what part of Earth is going to see an eclipse or whatever, that's planetary motion. But in that case, the orientation is a big part of it. And so now we're going to talk about rigid body kinetics. So now we are going to be able to differentiate between different parts of a body. And now we are going to be dealing with orientation. So the calculations involve orientation. Lost my eraser. So for tracking orientations, and that's going to be the main thing that we do now, the main change. We're going to use the same quantities that we used in circular motion. So we're going to use the angular quantities. Circular motion. Yes. No, we have only been doing particle kinetics. We did particle kinematics, particle kinetics, then we did energy, but still with particles. So these angular quantities are theta, that's the angular position. So rigid body's angular position. Then the rigid body's angular velocity, how do we represent that? Yep. Yes, omega, lowercase omega. So that's a rigid body's angular velocity. And then angular acceleration. What's that one? Alpha. Goldfish. That's a rigid body's angular acceleration. And what are the SI units for all of these? Angular position? Radians. Position is just radians. So that's just the angle that the thing's at. Angular velocity? Radians per second. And angular acceleration? Seconds. Yep. And there are two important things to notice about these. The first one is positive angular quantities always mean counterclockwise rotation. We're only going to be doing stuff in 2D, so counterclockwise is a reasonable way to describe it. When you go to three-dimensional motions, there's not really any such thing as clockwise or counterclockwise. You know, if you look at a three-dimensional motion from the front, it might be clockwise. If you look from the back, then it would be counterclockwise. You know what I mean? You ever thought about that? Think about it. So, like, look at a motion on the table. It's counterclockwise. If you were watching that motion from under the table, it would be clockwise. And so in 3D, that's not a useful way to describe it. So what this really is a simplification of the right-hand rule. So that's a two-dimensional, a 2D. Yeah, it does a million things, but that's one of them. What? So that's a 2D version of the right-hand rule. And the right-hand rule it's really just a way to relate the direction of a vector to the direction of a rotation. And so it relates the direction of a vector to the direction of a plane that's perpendicular to that vector? Okay, so if that's a plane, those two vectors are both perpendicular to that plane. And the right-hand rule works like this. So there's your right hand. Actual hand may vary. Okay, that's great. That's a great hand. No, I draw the line. Okay, and so the way this works is the thumb is always the direction of the vector. And the fingers are always curling in the direction of the rotation in the plane. Okay. So the thing that you said about coordinate axes, if you start your fingers at the x-axis, so let's say we have a coordinate system that's like x, y, z coming up towards us. Start your fingers at the x-axis, rotate them up to the y-axis, then your thumb is in the z direction. Yeah, then the vector, so if you're talking about a rotation going the other way, then according to the right-hand rule, that is related to a vector going the other direction. And so with this relationship, there are a lot of laws of physics and a lot of math that use that idea. But anyways, that's all just sort of a long-winded way of saying in 3D you have to think about rotation directions according to the right-hand rule, but in 2D it's just clockwise, counterclockwise. And what it is if you're looking at a coordinate axis coming out towards you, then the rotation is counterclockwise. Okay, so that's the first thing to keep in mind. Counterclockwise and clockwise is only a two-dimensional thing. In 3D, there's a little more to it. And then the second thing to notice about this is on a rigid body, so for a particle, you know, the position of a particle, velocity of a particle, acceleration of a particle, those are all defined things because a particle is just represented by a single point size object moving around, no length dimensions. But on a rigid body, that's not true anymore. Each point on the body has its own position vector, velocity vector, and acceleration vector. Okay, that's an important idea. So if you have something spinning around, well, you know, first think about something that's like a Ferris wheel. Okay, think about a Ferris wheel as a rigid body. At the axis that it's rotating around, that point doesn't have any velocity or any acceleration. It's staying right there, you know. But other points are moving around in a circle, and they're moving around in a circle at different speeds. Something close to that axis of rotation is moving slowly, with a small acceleration. Something way out at the end is moving fast with a big acceleration. So if you're talking about rigid bodies, you can't just say this is the object's velocity, acceleration, position. You have to specify what material point on the body you're talking about. But that's not true of the angular quantities, and that's a nice thing with in working with these angular quantities. Those angular quantities do represent the entire body. So the entire body has the same angular position, angular velocity, and angular acceleration. Those represent the whole thing. But there are relationships between the translational quantities and the angular quantities. So I'm going to do that just with an example problem. There are relationships between translational and angular quantities. Okay, so here's the example problem we're going to do. So let's say that there's a rigid body and it's rotating around an axis here. And let's say that the distance from the axis to the short end, the near end, is 0.2 meters. And from the axis to the other end is 0.6 meters. And let's say that this body has an angular velocity of 10 radians per second. And an angular acceleration in the other direction of 15 radians per second squared. And let's call this angular position well, let's just call that 0 radians. Then let's figure out so if this is the point A on the short side and this is the point B on the long side, what are the position vectors, velocity vectors, and acceleration vectors of these points A and B? Okay, so the idea is, this is stuff that you've already done before. If you think about the fact that every point on a rigid body is moving in a circular motion around its axis. So this point A is moving in a circular path like this. And this point B is moving in a circular path like this. Okay. So you want to go to the whiteboard and try this based on that information? Okay, let me know if you get stuck. Okay. So there are two circles. So if this is the object and this is the axis, then one is like that, and one is a lot bigger, like that. Okay. And so if we're talking about this point here, this thing has an angular velocity counterclockwise. So the velocity is this way. Is it speeding up or slowing down? How do you know that? Yeah, because omega and alpha, they have opposite signs, so the rotation's slowing down. So velocity and tangential acceleration are always going to be opposite each other. So here's the tangential acceleration. Centripetal is always towards the center, so here's the centripetal. And then talking about this point, it's moving this direction, so the velocity is this way. The tangential acceleration is opposite because it's slowing down. Centripetal is this way. And so now we can go through and, for A, if the origin is at that hinge, the position vector is negative 0.20. The velocity vector we can get with the speed, which is omega absolute value times 0.2. So that's 1 meter per second. It's in the negative y direction, so the velocity vector is 0, negative 1. The tangential acceleration is in the positive y direction, and the magnitude is the magnitude of alpha. What? 0.2. That's weird. What happens when you try to talk while you think about something else? Like waffles. Yeah. No, not really. I don't even like waffles. I was thinking about the next thing I was going to say. I don't like them. I don't know. I just don't like them. Yeah. That escalated quickly. Yeah, that could be. Okay, I'll try them. I'll be over at 11. Oh, really? Oh, that's interesting. So tangential acceleration is alpha times r is the magnitude. Alpha is 15, the absolute value. The radius is 0.2. So this is 3 meters per second squared. In the positive y direction, so as a vector, that's 0, positive 3. Centripetal acceleration is in the positive x direction. That's b squared over r, so 4 over 0.2 is 20. So 20, 0. And so the total acceleration is 23 meters per second squared. Any questions about that first one? Now the directions, also the magnitudes are going to be different for the point B. The magnitudes are going to be different because the R vector is different. So now for the point B, the speed is the angular velocity of 10 times the radius of 0.6. So that's 6 meters per second. And this time it's in the positive y direction. So the velocity vector is 0, 6. So notice, the directions of the velocities are different for the different points on the same body. But the magnitude and the sign of the angular quantities are the same. And then the tangential acceleration is in the negative y direction. The magnitude is 15 times 0.6. So that is 9, 0, negative 9 meters per second squared. And then the centripetal acceleration is in the negative x direction. The magnitude is 6 squared over, so v squared over r, so 36 over 0.6 is 60. So negative 60, 0 meters per second squared. Now add those up and you get the total acceleration of that point of negative 60, negative 9 meters per second squared. Any questions about that? Okay, so from looking at those angular quantities, the angular velocity and angular acceleration, we can tell the rotation is slowing down. What about the translational motion? Are those points speeding up or slowing down at that instant? How would you know? Not just the acceleration. Compare the part of the acceleration that's parallel to the velocity. That's the tangential acceleration. And so in this case, that's not too hard to do. So velocity and tangential acceleration in both cases are in opposite directions. So the rotation's slowing down and those translational velocities are slowing down. That's the case if there's a fixed axis. We'll see it gets a little more complicated if you have like a boomerang that's spinning as it moves, Boomerangs, yeah, I'm going to be throwing them while you try to do calculations. Yeah, exactly. It's like too much. Yeah. Yes, of course. My kids love that movie. Okay, let's take a 10-minute break, come back at 9, and we'll keep going. Okay, so now, so that's really all there is to the kinematics of rigid bodies, is just relating the translational quantities to the angular quantities. Yeah, so now we're going into kinetics. So Newton's laws for rigid bodies. Remember, I'm concerned that some of you may be squandering the opportunity to talk all the rest of the day and all the rest of your classes. So remember what's on the line here. So first is Newton's second law. That's the only one that we used for particles. And that says that the net force is equal to the mass times the acceleration, except now we know that the acceleration of a rigid body depends on what point you're talking about. Whoa. Paradigm shift, right? So what point are we talking about? Yes. Very good. Yes. So F net is equal to the mass of the object you isolate times the acceleration of its center of mass. It might not be the axis, right? This must be the center of mass, the acceleration of the center of mass. And the center of mass, we're not going to do any complicated shapes. There's an integral definition of center of mass that you have to use for more complicated shapes. For simple shapes, you can just think of the center of mass as the geometric center. And if you can find two different axes of symmetry, it's at the intersection of those two. It lies on any axis of symmetry you can find. And so that means if you can find two, it has to be at the intersection. So for example, a rectangle, the center of mass, here's a line of symmetry, here's a line of symmetry. And so the center of mass is there. And a circle, you can find infinitely many. But no matter which two you choose, they intersect at the center. So that's the center of mass. And like car commercials where they use crash test dummies? You've seen that symbol before. Well, let me tell you. Yeah, I'm not going to give him a face, but yeah. But the idea, so why do crash test dummies have these drawn, like have you noticed that symbol is all over them? Like that's kind of the one thing they use to signify that something's a crash test dummy is every part of its body has this symbol on it. Well, that symbol shows where the center of mass of that part is. So if you're watching like a crash in a high-speed video, your camera can track the motion of the center of mass of all those pieces. And since now you know that the most important equation for kinetics is Newton's second law, which relates to the center of mass, those are there so you can measure the acceleration of that point on the video and then do the physics of the forces based on the center of mass. Cool, right? Yeah. I think so. Now you do. Yeah, exactly. Now you know it's important. Um, with rigid bodies, so Newton's second law is the only Newton's law for particles. With rigid bodies, there's a second one. Well, you know, this wasn't one of Newton's original laws, but it is derivable from Newton's second law.
It's not like
Right. It's implied by his second law, but he didn't make this jump. But there's a second equation, and I'm going to call that the rotational version of Newton's second law. And so I always abbreviate that RN2L. But nobody you write that to is going to understand what you're talking about, except me. Yeah, right. They won't know what you're talking about. Yeah, then they still won't know what you're talking about. But this is what that equation is. I mean, you'll see why, you know, the similarity to Newton's second law. So it says that if you add up all of these things called moments about the point A, so this is the sum of the moments about A. That adds up, that's equal to the mass moment of inertia about A times the angular acceleration. And the cool thing is, well, let me, this point A has to be one of two things. We're only going to use one of these, but it has to be either an axis of rotation, in other words, fixed in the coordinate system. If you have a seesaw or something, that hinge is fixed to the ground and your coordinate system is fixed to the ground. So the hinge is fixed in your coordinate system. Or it could also be the body's center of mass. That makes the calculations a little harder, though, and we're not going to worry about that. Okay, here is the thing. This thing, the sum of the moments, you can think of as like an angular version of a force. You can think of that as the angular version of F net in this case. The mass moment of inertia is the angular version of the mass. This is obviously like an angular version of acceleration. And so this rotational version of Newton's second law has the same format as Newton's second law does. It's just dealing with all angular quantities instead of translational. Okay, so I'm going to write out a table here. So this is just going to compare all the sort of analogous things between translational motion and angular motion. So translational, angular, or rotational. Center of mass. Yep. IA is the mass moment of inertia. IA is the mass moment of inertia. And you can think of that as an angular version of the mass. What? Well, I'll talk about that, but you know how in the Olympics, in figure skating, at the end of their routines, hey, do you know why they do their spins at the end of their routines? So they won't be dizzy, yeah. And that never occurred to me, but it hit me like a lightning bolt, and then I was just obsessed with seeing them do routines where they had to do their spins first and then go do the jumps and stuff. But anyways, that's a digression. But at the end of their routines, they start out spinning, right? Slowly. And then they pull everything close, and then they spin really fast. What they're doing is, so they're not changing their actual mass, but they're changing how far away from their center line their mass is distributed when they pull their arms and everything. And what that's doing is changing the angular version of their mass. They're pulling everything close to the axis. That makes it easier to rotate, and that's why they spin. Rhea can confirm. Thank you. Yeah, never once do they pull their arms in and go slower. Okay, so first, position. If you're talking about translational motion, that's a position vector. If you're talking about angular motion, that's theta. Second is velocity. Translational is the velocity vector v. Angular is omega. Third, what am I going to say here? Yep, acceleration. So that's the vector A, the translational acceleration. Angular is goldfish, alpha. And now we get to the kinetic things. Those are all the, time is the same for both, so I'm not even going to write that. But now we get to loads. For translational, that's a force vector. For angular, that's a moment out of point. And we'll talk about what that is. Sometimes you hear that called a torque. In physics, people tend to treat those as synonyms, and in engineering, people tend to use the word torque as a specific application of moments. But like a moment, like when you turn a screwdriver, you're applying a moment to the head of the screw. So a moment is something that causes turning. Then fifth is a measure of inertia. So what determines how hard it is to make something translate? It's its mass. That's what mass does. So if something with a big mass is very hard to accelerate, something with a small mass is easy to accelerate. And angular is I sub a. That's the mass moment of inertia. What that says is if you have a big mass moment of inertia, it's hard to get something rotating. If you have a small one, it's easy to get it rotating. So that's the example of it's hard to get a figure skater rotating if their arms are stretched out. It's easy if they're pulled in. And then the last thing is the equation of motion. If you're talking about translation, the equation of motion is F net is equal to the mass times the acceleration of the center of mass. If you're talking about angular motion, then the net moment about A is equal to the mass moment of inertia about A times the angular acceleration. And it has the exact same form. So you should never forget the form of this equation. It's just like this one.
Is that a sub, or is that like?
No, that's multiplied by the angular acceleration, just like this. No, that's fine, but we should get this straight because it'll be a lot easier to remember if you notice that these are the exact same form. In both cases, you add up all the loads, and that's equal to the measure of the body's inertia times the body's acceleration. Oh, yeah, it's amazing how it works. Although, I mean, I guess this is derived from that, so in that way it makes sense. Any other questions about those? So it makes it, if you keep these analogies in your head, it's a lot easier to remember all this stuff because in a way, all this new angular stuff we're doing is just a new application of all the relationships you've seen. You can even, I'm not going to put it in this table, but you can even use, well, let's put it in. Why not? So these equations, V final, so these are the constant acceleration equations. So they say V final is equal to V initial or V sub 0 plus A E. If you have constant angular acceleration, then omega final is equal to omega 0 plus alpha t. For translational, P final vector is equal to P initial plus V initial times time plus 1/2 A t squared. And so what does the angular one say? Yep. 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 Yep, exactly. So if you remember these analogies, you already have all this stuff stored in your brain. There's no reason to use more storage space, Okay, so before we talk about yep. Before we discuss rotational Newton's second law. We need to define these two things that I've mentioned, but only sort of loosely. We have to define the mass moment of inertia about a point and the moment about a point. So I'm gonna define those two things, and then we'll use them in the equation of motion. All right, so the mass moment of inertia about a point. That's a lot to say. And that's always represented as a capital I sub A. People usually just say moment of inertia, so this is implied. This is implied. There are other types of moments of inertia, so if you can't tell from the context, you know you need to have those words in there. And this is a measure. This measures how hard it is to get something rotating. How hard an object is to get rotating. For example, Summer Olympics now. So gymnasts do, lots of flips. And so if you're going to do a double flip, there are different ways you can position your body to do it. And some ways give you a ton more points than other ways. And why is that? So, right. Okay, so don't treat people like objects. Yeah. Yeah, okay, so that's one way, and then this is the other way. Yes.
I thought the first one was a leg, and then the second one too.
Okay, so you get a lot more points for doing it layout than you do for doing it tucked, because it's a lot harder to get your body rotating in this position than it is in this position. And because of that, you have to get a lot higher to finish two flips in this position than in this position. He's doing an entire flip like that. And if you watch someone do it, like even without knowing anything about gymnastics, you're like, wow, that looked high and difficult. And if you watch someone do it like that, if they really tuck in tight, they rotate so fast they really don't have to get, I mean, that's still hard to do. But, I can't do it then. I know, exactly. It's easier to say than do, but it's a lot easier to do it tucked than it is layout. So what's the difference? Mathematically, the difference is the mass is distributed farther from the axis of rotation. And so if you do that, that's a big moment of inertia. And that makes it hard to rotate. In the tuck position, the mass is distributed near the axis. Closer to the axis. And so that's a smaller value of I sub A, and that's easier to rotate. The integral definition of mass moment of inertia I sub A is equal to the integral over the whole body of rho squared dm, where rho is the distance of this infinitesimal mass dm to the point A, which is that axis of rotation. Okay, so you can see, like, if you have the same mass m, like, just think sort of roughly about applying this integral definition in those two gymnastics cases. For the tuck case, all of these rows are pretty small. Imagine breaking up the body into all these small chunks of mass. Don't really break the body up into small chunks of mass, but just mathematically. Each one of those DMs is close to the axis of rotation. Okay. And so when you add up all those, so all those row values are small. And so add up all these rho squareds times dm, you get a small number. Here, there's some DMs that have small rho values, but there's also some that have pretty big rho values. The head is pretty far from the axis. The feet are pretty far from the axis. And so when you add all these up, you're going to get a lot more, a much bigger value of I sub A. And none of those, when you add them up, can cancel each other because rho squared obviously has to be positive. Mass is positive. And so you get a bigger value of that integral. Yes? Just the same way that you can break up a function into small increments of x. Like if you think of what an integral is just breaking something up into tiny pieces and then adding up those tiny pieces. Yeah, I can show you. Yeah, let's stop there for today. And so this is sort of the idea. Like, let's say we want to calculate the mass moment of inertia of. No, let's do it for a circle. I think that'll be faster. Okay, so let's say that this distance is capital R, and the mass is m. And then to do the integral, we'll break it up into, let's say these are infinitesimal masses dm, are these little rings. And so I sub A is going to be, well, let's think about rho squared times dm for that infinitesimal ring. The way to think about that is think about disconnecting this ring at one end and straightening it out into a long, skinny rectangle. Okay.
Is that it?
Trapezoid, but it's infinitesimally thin, so the difference as you get smaller and smaller between the trapezoid and the rectangle goes to 0. Yes, in this case, yes. And so the thickness we'll call dr. The length is the circumference, so that's 2 pi r. The total area, so the area is pi r squared, pi big R squared. And so the mass for every bit of area, think of the mass per area is m over pi r squared. This is where it's going to get a little messy, actually. But anyways, the mass is equal to the mass per area times the area, right, obviously. So we can write mass equals mass, right. Well, so I'm just doing that so I can rewrite this in terms of area instead of mass. Okay, so then our dm is the mass over pi r squared times dA. Okay, this is our dA. And so we end up with this integral. We can pull this out, m over pi r squared. No, that's just an increment. That's the thing that we're integrating over. That's our little tiny increment of mass. And this is equal to r squared times 2 pi r dr. And we're integrating this we can cancel the pi's. And pull the 2 out here. And then we have r cubed dr evaluated from 0 to big R. This is not clearing this up to anybody, I don't think, but looks like we'll at least get the right answer. So we get 2m over r squared times r to the 4th over 4, evaluated from 0 to r. So you get mr squared over 2. I don't know. That's how you do it. And that is the formula for the mass moment of inertia of a disk, of a circle. No, you're not going to ever have to do this, but I mean, I guess it is. Coming up with the formulas is always this complex, but you won't ever have to do that. Right. Okay, sorry, I made you go a little over. See you Friday.